Hey, welcome back. Today we're going to be talking through the mechanical energy of a satellite in a circular orbit. This is for AP Physics C mechanics, and it's something you're expected to know, and once you see it and think about it, maybe practice it a bit. You can use this on a test if you get a test question about this. So let's go ahead and get started with it. The question that we have today is, what is the total mechanical energy of this satellite in the system? So let's think about it. There is a speed here, a tangential speed. And so the satellite, maybe it's the moon, it's moving around in basically a circular orbit. And so there are really two different types of energy. So we could say the sum of the mechanical energy here, or sometimes it's written as total mechanical energy, is equal to the kinetic plus the gravitational potential energy. And so we know something about these things. We could say the sum of the mechanical energy, the total mechanical energy that we have, well, that's 1/2 mv squared minus big G m1 m2 over r. And that's not r squared, that is simply r. And what am I writing here? This is universal gravitational potential energy here, and I've done an entire lesson on this. If you need more background information about that lesson, I'll put a link to that in the upper right about now. But the reason why we do this is because sometimes we just deal with things that are too far away from the surface of the Earth that we can't use m times g, where g is 9.81. We have a need for a more universal system of figuring out what potential energy is, and this is how we go about doing it. Okay, and there are a couple other things that we can talk about here. I'm going to draw a force here, and I'll do this in a different color so you don't think that I'm drawing a free body diagram with just a force and a speed on there. That's a bit odd, fair enough, but I do want to point out that there is a force. There has to be a force going towards the center. In fact, we know this object is moving in a circular path, so the sum of the forces in for this object is equal to just the force due to gravity. That's all we have, right? That's the only force in that plane, in the in and out plane. And we know the sum of the forces in is equal to mass times acceleration. That's Newton's second law. And this strategy I call the sum of the forces strategy. So we can say the force due to gravity, in this case, is causing that circular motion. Now, because it's circular motion, we need to do something specific with this. This is centripetal acceleration. That's a special type of acceleration, so we're going to call this vt squared over r. That is on your equation sheet, and we do know Newton's universal law of gravitation is going to go on the left. So let's go ahead and see what we have here. We've got Newton's universal law of gravitation on the left and the sum of the forces strategy on the right. Notice immediately that our radius goes away and one of the radii on the left side. Okay, and at this point, it's really tempting to get rid of one of the masses on the left side and the mass on the right side. That would be the mass of the object because it's going around in a circular path. But what we're going to do instead is something a little different. Let's multiply by 1/2 right here and multiply this by 1/2 as well. If we do that, this ends up being 1/2 mv squared on the right side. So this becomes kinetic energy. Right? That is able to feed into this right here. But we also know that it's equal to this. So check this out. We can actually sub this in. We can actually sub in the left side. This left side I'm labeling right now and sub it in because it actually looks pretty similar to the brighter red color that we have up above in terms of common terms. I mean, let's think about what we have left over. The mechanical energy is equal to 1/2 g m1 m2 over r minus g times m1 times m2 over r. Well, let's combine like terms. Basically, we've got that whole thing is a set of like terms with the exception of a number. So we can say like the mechanical energy is equal to g times m1 times m2 over r, and the first term has a 1/2 and the second term has a -1. We have a sum here. We can say the sum of the mechanical energy is equal to a -1/2 g m1 m2 over r. And that's what we have. I could combine the two down here if I wanted to, and erase this out in front. But that's what we have, or you can draw it out just to kind of make it clear what we're dealing with. Actually, either way is going to be fine, whatever you prefer. But the idea is this is going to be the sum of the entire energy for a planet. Now, I want you to think about mechanical energy for an object that's moving in a circular path. Now I want to talk about a couple things. So check it out. This is negative. This is negative. And I want you to think about what that means. It turns out that we were comparing kinetic energy, which is going to be positive, that cannot be negative, and our universal gravitational potential energy, which is negative over here. So it turns out that the gravitational potential energy is more negative than the kinetic energy is positive. And that actually makes sense. Our answer should be negative for a bound system. Because if you think about it, if we came out with a positive answer, that would mean that there would be more kinetic energy than there is potential energy in a magnitude sense. And it wouldn't be a bound system. The object in orbit would spiral out and leave orbit. So it must be the case, if we have a bound system where you have a satellite going around on a circular path, it must be the case that we should get a negative answer for the total mechanical energy for the system, because that's going to give us our bound system where the object is actually in orbit around the planet. I do want to say I've done lessons on an entire year of physics as well as most of the ideas in AP Physics C mechanics. So if you have any questions or comments down below, please let me know. And I hope you all have a great day. Take care.